All right, thank you for coming this afternoon. Today we're going to be talking about area depth strain analysis for seismic interpretation. And first we'll start with a brief overview of Structure Solver software. And so essentially it's based around simple 2D interpretation system that allows us to perform quantitative structural analyses in relatively flexible and quick fashion. And in essence, it's really targeted at solving complex structural problems, but common ones. And so these are really fundamental things like correlating horizons across faults, understanding the timing of structures, as well as understanding where faults go at depth. And today we're going to be really focusing on the area depth analysis technique. So the software itself has tools for structural restoration, modeling, and area depth. And today we're going to be talking about the area depth tools. And so kind of the principal outcomes from this method in particular are such as looking at computing depth to detachment from an interpretation. We'll look at some cases where we have incomplete interpretations and then use that initial interpretation to compute the fault location at depth. Gives us some insight into strain within reservoirs, as well as has some ability for QA, QC, and assessing balance in the interpretation. And so it's very complementary to the other tools that we present in Structure Solver, but then this one takes a slightly different approach of essentially beginning with some interpretation and then extracting the kind of quantitative information from that geometry and moving forward. And so in terms of a more overview of our the value proposition, basically all of our tools are really designed to be rapid for use. And so we are trying to alleviate specific bottlenecks that have hampered structural analysis in the interpretation process, like long project setups or the requirement to have a high level of expertise in specific structural settings in order to actually access the available software. And so by having something that's flexible and easy to use, we're really after opening and democratizing these methods for all geoscientists who are working in interpretation projects. And in essence, we're trying to avoid these common errors in interpretations and get a deeper degree of insight into the seismic data that interpreters are working with. So today's method that we're looking at is area depth strain analysis. And we'll look at it from the theoretical perspective first and kind of look at the method and how it was developed. And then we'll get into some specific examples and then finally wrap up with a case study from the western Gulf of Mexico and the Mexican ridges. But essentially, area depth analysis comes down to a really rather simple set of assumptions that during deformation, a given structure will maintain area. And so the area that you see in a fold in, for example, a seismic section, and what we're looking at here is a kinematic forward model of a fault propagation fold where we have some observable folds. And the concept is that the area of a fold that you could measure from an interpretation or a seismic section should be equal to the amount of area displaced above the detachment. And you don't directly observe this, but what you can directly observe is that fold area. And so in essence, that amount of displaced area is going to be a function of essentially the horizon depth above the detachment, as well as the amount of displacement. And so the original premise was that if you can observe that fold area and you know something about the original depth of the horizon, say in the footwall, where this yellow dashed line is, you can measure that fold area and use that depth, so the H right there, to then compute the displacement of the structure. And so that was sort of the original early 1900s look at the area depth relationship. And so we've actually, in more recent studies, been able to expand on that to then use that relationship to compute where the detachment is located. And all of this is with relatively minimal kinematic assumptions. So just constant area displacement, and that one of the upshots of this is that the bed lengths aren't required to we're not assuming that they're maintaining length during deformation. And we'll circle back to this, and that actually is the key factor that allows us to estimate changes in bed length and relate that to strain. So in practice, the way that the method is carried out is that we're, as we mentioned, measuring these fold areas and relating it to this displaced area. And then the assumption is that everything in sort of this intermediate zone really isn't changing. And you basically have this displaced area passing through the structure and then up the ramp to create that fold. And so in order to compute the displacement as well as the detachment depth, we employ a area depth graph where we begin to plot fold areas as a function of their depth. So area is on the horizontal axis, and then we plot the depth along the vertical axis. That's what's shown here. So for our first horizon in green, that's horizon 7, that plots right up there. So this is the largest fold area in that particular model. And then as we go through, we're just measuring these fold areas, and the observation is that for pre-growth horizons, and this is where the constant displacement assumption comes in, they should all have that same amount of displacement. But because what we see is that those fold areas decrease with depth towards the underlying fault, we end up with this linear relationship defined by our constant area assumption. And so when you go in and actually plot these, what you're doing is circumventing the need to know what that displaced area is. And you get an array of horizon areas where we've got 7, which was our largest area, decreasing to the blue sort of in the middle, and then the orange one at the bottom. You can see they get progressively smaller, but because they've all experienced that constant displacement, those fold areas are only varying as a function of depth. And so that's why we get this linear array. And if we do a linear best fit, we get 2 things. One, we get the detachment depth, or the predicted depth where those fold areas go to 0, which gives us the depth of the detachment right there and the intercept with the depth axis. And then the slope of the line is essentially this equation. So the change in fold area over the change in depth gives us the displacement. So that's the linear fit right there. And so because this is an area balanced forward model, it's a perfect line for all of those fold areas, and we get a nice estimate of the detachment depth. So in practice, the way that this is applied is somewhat removed from how people are used to looking at using bed lengths for restoring and estimating displacement. And so what we'll do here is just take one more quick look at how we're going to do this. In this case, we're looking at an extensional forward model that was created in Structure Solver. And we've had a few previous presentations on this, but if you're not familiar, structural forward models are essentially a way of computing the geometry of a fold or a folded horizon from the shape of the fault, assuming constant area during deformation. And so this is a area balanced forward model here that was created in Structure Solver that has a known amount of displacement. So this model has 375 feet of extension along that listric fault, and then this is the computed fold shape that arises assuming inclined shear and extension across that listric fault shape. So if you were looking at something like this in the seismic and you wanted to apply it to apply an area depth graph to either compute the amount of displacement or the detachment depth for the structure, say you hadn't imaged that flat detachment, the way that the method works is that we start out by putting an area depth graph right over the section. And then we're measuring these fold areas relative to the depth of these horizons, the regional depth. And so that's defined as the undeformed or pre-deformation depth of a horizon. And so the way we implement this is what we refer to as a regional limit. So on either end of the structure, we have these regional limits that essentially define the depth in the footwall and the regional depth in the hanging wall. And then for this particular method, the flat detachment method, if we just draw a straight line from those 2 depths, that gives us our regional depth line that we measure the fold area relative to. And so for this first blue horizon, that shaded region is plotted on an area depth graph. So it's bound at the bottom by the fold shape, and then limited at the top by the regional depth, so the kind of pre-deformation depth of that horizon. And so there's our square right there, plotted at the regional depth with the appropriate amount of area. And this is just showing that same amount of area at the regional limit that was displaced along the detachment. So we repeat this process for a series of pre-growth horizons, and you can see that they begin to stack up along that linear trend that we just talked about, but those fold areas are diminishing as they get closer and closer to the detachment. Finally have a very small amount of area right above the detachment itself. And by doing a linear fit, we get the computed displacement, which you'll notice this. So this is coming from just those fold areas. You'll notice the computed displacement is reported here, and it's 375 feet. And that matches our forward model, the input displacement exactly. And so that's computed from the slope of that line. So the variation of fold area is a function of depth. And then the intercept of that best fit with the depth axis gives us the detachment depth. And you can see that that dashed blue line lines up exactly where the model is. And so it's a very robust method for quickly determining displacement and detachment depth. And so those are some of the immediate things that you get out of area depth plot. And so we'll look at this case study. We'll kind of conclude with this case study at the end. But what I'll do for now is actually run through a series of examples of applying area depth in practice and some of the potential applications. And so we're in Structure Solver now. So this is an example from the Sierra Pampeanas in Argentina. It's a basement-involved fault propagation fold, and we've got some interpretation over it. There's a kind of siliciclastic section that overlies a basement section, and it's not entirely obvious, where that fault would go with depth. There's a very strong reflection within the basement. That's sort of the most obvious place to assume the fault goes, but you can easily imagine a situation where there wouldn't be, that reflected energy, and all you would really have to work with in terms of defining the structure is sort of the better resolved shallow part of the fold. And so the premise, one of the fundamental things you can use area depth for is determining where those faults are going at depth. You may see it in the shallow part of the section, but understanding the deeper geometry is essentially unknown. So what we can do in this case is start with our basic interpretation. We have a series of horizons that have been interpreted, as well as the upper part of the fault segment. And so to create an area depth graph, it's as simple as starting with our interpretation. We'll can define colors, pen width, so on. And we're going to use our proprietary method, the fault trajectory method. And this is an advancement over the depth to detachment method, which is the classic approach to area depth analysis, where you assume that the structure is underlain by a flat detachment. And that was a traditional limitation of the method, that it really was best applied to detachment folds, not structures like this, where the footwall is consistently deeper than any of the hanging wall horizons. And so by generalizing the equations behind the area depth method, we're able to maintain that same constant area assumption, but then it allows us to deal with structures where the depth in the footwall is greater than the depth in the hanging wall. So we can actually compute fault dip now. And so that's why we're assuming that the fault crosscuts the stratigraphy at depth. So this ends up being a much more flexible approach than the standard flat detachment method. The one limitation here is that, before I get too far ahead of myself, is that you'll notice that there's also some regional dip on the structure. So if we actually look at the dip of the footwall here, the interpreted footwall horizons, we can see that there's somewhere between about 4 and 5 degrees of regional dip. The entire structure is dipping off to the foreland. And so assuming that these are kind of the undeformed footwall locations, that's a regional dip that we're going to need to deal with in order to correctly compute those fold areas. So we can handle that by rotating the section to back out the amount of dip on the in the footwall. And so you can see here that I've got about 4 degrees of rotation, and these are the rotation template lines, and they're about parallel to the footwall. So we'll rotate the section. And so now we've removed the regional dip, and I'll explain why this matters for area depth analysis. So we're going to create our area depth graph on the rotated section. And so we can begin to add points to our area depth graph. So this is the same display that we were looking at before. And now we have our regional limits on the left and right. The red line running through the middle of the structure is the depth axis. And then each of these squares are the plotted fold areas for those horizons, plotted horizontally as a function of those fold areas. So I can go in and actually look at how the software is measuring those fold areas. And the reason that we need to we need to deal with that regional dip is that the software and our method is to use the footwall depth of the horizon as representative of the regional depth, and then have the hanging wall position represent the deformed depth. And so assuming that all of these horizons are moving parallel to the underlying fault, the difference in the depth at the regional limit in the hanging wall versus the footwall allows us to compute the vertical throw on the structure and take that into account when we measure these fold areas. And so you'll notice, in contrast to our extensional example with the flat detachment, where we were measuring the fold area back down to the same depth in the footwall and hanging wall, here we're measuring those fold areas relative to the footwall depth. So you can see where the shading stops at this thin dashed line below each of those folds, and then extends up to where the fold has been interpreted. And so that allows us to account for the vertical displacement above that dipping fault plane. So we'll add in the rest of the horizons. We'll extend our workspace. And so now reported out at the left, we have the displacement on the structure. So it's about 1.2 kilometers of total shortening. And that is coming from the slope of our linear fit. The intercept of the linear fit with the depth axis, I'll just use a horizontal ruler. So the depth intercept is right about there. And you'll notice if I come across, the depth intercept is defining the depth of the fault. So the addition for the fault trajectory method is that we're taking into account the throw on the fault. And so we're using the displacement from the slope of the area depth graph as well as the throw. So the difference in the depth of the footwall versus the depth in the hanging wall to also get the dip on the fault. And so we project that upward into the structure along this dashed line, and you can see that it lines up with that strong basement reflector, confirming that for this interpreted fold and fault geometry, the deeper extent of the fault is at a slightly shallower dip than the upper segment and follows right along that reflection. And so what we're seeing is that this interpretation is consistent with a dipping fault plane in the basement of about 18 to 20 degrees. And so the things that we also get out from this are, of course, the displacement. So we mentioned about 1.2 kilometers of shortening. And what's important about that is the constant area displacement. And so this is different than restored balanced cross sections, where you assume that the bed length is constant and use the bed length, the difference between the length of a bed, measuring the length all the way along the bed itself versus the length of the section, so the present day length of the structure, in order to estimate the displacement. And so that requires that the bed length be maintained during deformation. So here we're just using those fold areas to estimate the amount of displacement. So it doesn't require the bed length to be constant. And so that gives us the advantage of being able to compare the displacement from the fold areas to the displacement that one would estimate just based on the bed lengths themselves. And so what we're reporting here is the displacement that you would get if you simply removed the slip on the horizon and flattened out the fold. And so that displacement is about 1 kilometer for the purple horizon. So it actually underestimates the total amount of displacement on the structure. And so what that indicates is that the bed is actually shortened internally due to subseismic deformation that we're not seeing in this section, because there isn't really a significantly different way to interpret that purple horizon in order to include the deficit in bed length in order to increase the displacement to match the constant area displacement. And so what we do is we graphically show that by these small vertical lines across the vectors themselves. And so the full length of this vector matches the vector on the detachment, and that is the constant area displacement. So that's 1.2 kilometers of shortening up the ramp there. But then we've got these little tails, these little these small lines right here, and that represents the displacement that one would get from the bed lengths. And so we refer to that as the nominal displacement. So that's reported out here with the rest of the various displacement parameters. And so what that tells you is that essentially down here, there's this small discrepancy between the constant area displacement, so that's the full length of the vector, and the bed length displacement, which gets you right there. And so that small difference is attributed in this case to layer parallel strain. And so that shortening in the bed length is graphically shown by those difference in those two vectors. So that's about a 1% difference in the displacement. And that means that the bed has decreased in length by about 1%. And what's interesting is that, one way to look at this is that it's a potential indicator of the line length balance in your section. If you think that the structure maintained bed length during deformation and all the beds should be constant, the layer parallel strain can potentially be an indicator of line length imbalance in the section, and that you might want to revisit how the structure has been interpreted. On the other hand, and this is much more likely in many cases, is that those beds have actually changed length during deformation. And what we see for this particular structure is that those percentages have a pretty consistent trend where they're pretty much negligible down here in the lower part of the structure, but they increase to about 4% layer parallel shortening, negative 4%, at the very top. And if we look at the structural character, what we see is that for the purple horizon, there really isn't a lot of folding. Pretty much everything in the structure is sort of parallel to the overlying beds, and there's quite a bit of offset on the fault. So if we look at the intersections of those horizons, there's our intersection for the purple horizon, and the amount of slip on that fault is 1.2 kilometers. So there's a lot of slip on the purple horizon. Whereas if we contrast that to the green horizon at the top with 4% layer parallel shortening, there's only about 700 meters of slip on it. And so what we see in the hanging wall is that there's quite a bit more folding here. And so kind of the qualitative structural style sort of fits with this idea that the more this green horizon experience quite a bit more folding than the underlying purple horizon. And it turns out that this has to do with the fact that this is a fault propagation fold where our purple horizon experienced most of the strain isolated along the fault and manifested as fault slip. Whereas at the green level up here that was above the propagation level, the fault slip was slightly reduced, and some of that total strain was partitioned into the development of that fold, which gives us internal shortening of the bed itself. And so there's a substantial amount of information that can be gleaned from just creating the area depth graph on its own. The fault trajectory method also has substantial flexibility in terms of measuring changes in fault geometry. And so this steps away from the displacements itself. And if we're just looking at the relationship between the shape of the fault and the shape of the fold that we've interpreted, what we can do is by changing the analysis limits of the area depth graph, you'll notice that we get a new different computed detachment depth for a different position in the structure. And so what you'll see is that as we come up the fold and look at a different part of the fold geometry, so we'll display these fold areas, we're measuring different fold, a different part of the fold at a different amount of throw, the computed detachment location changes as we change those analysis limits, and you notice that it actually follows that change in the fault. And so we can actually use this method to map out changes in fault geometry underneath the fold just from those fold areas alone. So I'll change the color here so you can see this a little bit better. But as I change those analysis limits, the computed fault depth as well as the dip, which is being computed right at that point, changes depth and dip. And so this is just, the dashed line here is really just the projected extension of the fault into the structure. And as we change those analysis limits, it recomputes dynamically the position of that fault based on the change in those fold areas as you sweep through different parts of the structure. So this can be, the practical upshot of this is that if you only have a few of these horizons, you can use it to map out a likely fault envelope that is consistent with the shape of the fold as it's been interpreted in the structure. And so to discuss the strain aspect a little bit more, we'll take a look at this example from the Niger Delta. And so we've already got an interpreted section. The seismic data is obviously very good and clear in this case, but it provides a good case study on this concept about the change in bed lengths during deformation. And so what we can do, in this case, we'll use the flat detachment method because the kind of key defining observation about whether or not you should use one versus the other depends on the if there's any kind of depth difference between the footwall and the distal hanging wall. So for example here, if we draw a horizontal line across the section for that orange horizon, you can see that the structure essentially, those horizons essentially return to the same depth in the footwall as in the hanging wall. And so that in itself generally implies a flat detachment for the structure. So we'll continue adding horizons to our area depth plot, starting from the bottom. So the multicolored horizons are following on this linear trend where the fold areas decrease with depth. But you'll notice that as we go upwards into these pink horizons, there's a change in those in that fold trend in terms of the fold areas. And what we're actually seeing now in this case is the indication of a growth section. So as we discussed in the beginning, the normal expectation for pre-growth horizons that are used to compute the fault displacement as well as the detachment depth is that fold areas are going to diminish towards the underlying detachment. And that is certainly the case here, where we have the greatest fold area at this peach horizon that decreases downwards linearly as a function of depth to the blue horizon where we have the smallest fold area. But for this overlying interval, the fold areas actually decrease towards the surface instead of towards the fault. And this is generally a characteristic of growth horizons. And the reason for that being that these horizons get progressively younger towards the surface, and they were deposited syndepositionally. So you see that they're thicker in the footwall than they are in the hanging wall. And so they've actually been deposited as this fold was growing. And that break between the pre-growth and the growth strata or synkinematic strata is indicated by that inflection point where we go from fold areas increasing downwards to fold areas decreasing downwards to fold areas that decrease upwards. And so as long as we have enough pre-growth to define that linear trend, we can compute the displacement on the structure. In this case, it's about 175 meters of shortening along that detachment. You can see that those growth then have a computed amount of displacement for each of those horizons. And so not only have we been able to quickly define where the transition from pre-growth to growth is located, but we're also getting the displacement history on the structure by first computing the intercept of the detachment, and then the displacement for each of these growth horizons is computed based on the slope of the line from each growth horizon to the detachment depth. And so that gives us the change in displacement over time. And you can see that this earliest growth horizon experienced most of the total displacement. And then at the more recent time, the less folded horizon has barely any displacement at all. And so this is where the area depth actually begins to give us some information about the displacement history too. And again, in this structure where this is sort of similar to the Argentina case in that we also have an array of layer parallel strains reported. And so for the cyan horizon, there's only about 1.5% shortening, so negative 1.5% layer parallel strain. And you can see that the displacement from the fold area is almost the same as the displacement from the from a constant bed length computation. But as we go upwards in the section, those strains really begin to increase and are dramatically higher for the peach horizon that is above all of where these faults tip out. And so the fact that these faults tip out below that horizon are pretty indicative of a fault propagation style of deformation. But what's interesting, again, is that we see the highest amount of layer parallel strain. So again, that's change in bed length during deformation for the horizon that is essentially purely folded. Whereas if we look at the cyan horizon down here that has relatively less folding, but more fault slip. So again, we can look at the slip on each of those faults. So for horizon A, the cyan horizon, that's 500 meters of fault slip that diminishes to about 100 meters of fault slip on the brown horizon. But these are the brown and the pink horizons are the ones with about 7 to 8% strain on them. So essentially they've accommodated all of this fault slip as folding and internal strain, whereas the cyan horizon has been purely offset along those faults. So the fault slip takes up most of the kind of total strain in the system. And so there's a significant amount of information in that, and that you potentially expect maybe more fracturing along the forelimb of this structure or distributed throughout that bed than you would away from the fault on these cyan horizons. And just in terms of kind of bringing this full circle back to looking at the forward model, so our estimated displacement from these fold areas, and again, this was interpreted by hand, so that gives us about 775 meters of displacement. The area depth method is entirely complementary to structural forward modeling. So this is the same structure, same seismic section, and in this case, we've created a very simple structural forward model. So we've essentially simplified out those two back thrusts that we saw earlier to create a very simple kind of continuum model to understand the evolution of this structure as well as the kind of structural kinematics. And so if we, the general approach, this has been covered in other presentations, but essentially what we've done is create a forward model that fits the seismic data by adjusting the fault. So this is the fault tip using a tri-shear algorithm. And so we've played around with the location of the fault tip as well as the total amount of displacement on the structure in order to create something that forward model that fits the seismic data as closely as possible. And what we see is that from these forward models, one of the outcomes that we get are the total amount of displacement on the structure. And so here we're estimating, this is the total amount of shortening estimated by the forward model is 880 meters, whereas when we were looking at our area depth graph, we had about 775 meters, or only off by about 100 meters of total shortening between the two methods. And part of that discrepancy is probably due to how we're dealing with the back thrusts are entirely accounted for by the hand interpretation, whereas in our forward model, we've simply simplified through them. And so we may be overestimating the shortening in the forward model versus the area depth method. But in any case, the two methods are entirely complementary because one of their fundamental assumption is simply that area is maintained during deformation. And so you can use both of these methods as essentially a kind of a independent check on one another in terms of the computed detachment depth. You'll notice that the forward model estimates the flat detachment underneath the structure. So again, we arrive at that computed detachment by changing the geometry of the fault model until it matches the seismic data, and the computed depth there from the forward model is about 6.7 kilometers, whereas the area depth method applied to this interpretation gives us a computed detachment depth of 6.7 kilometers. So the two are entirely complementary in terms of what you get out and providing sort of independent estimates of the same parameters. So the final example that we'll look at before we quickly go through the case study is the situation of what happens with salt. So, we talked a lot about constant area during deformation. And so what's the implication for something where you actually have salt moving around and messing with the total amount of area that you have in a structure? So this is a Keithley example from the Keithley Walker fold belt from a paper by Hudek. And so we've completed an interpretation based on, it's high quality seismic image, fairly straightforward. We also used flexural slip to continue some of these horizons off where the imaging isn't as good. So if we'll hide a few of those quickly to show you the kind of quality of the seismic data that we're working with. Let's see, so we'll hide. So you can see that, so this is our interpretation. You can see that the image gets wiped out underneath this salt tongue, but by using flexural slip, we can essentially project the rest of that fold limb into the limb where the imaging isn't as good. And so we can actually create an area depth graph for an entire fold train. So it's just a matter of adding those horizons. So we'll use the flat detachment method. And so the flat detachment method is a bit of a misnomer in the sense that it doesn't require, it can handle a regional dip in the sense that if you have like basinward tilt on the detachment, that's perfectly acceptable. It's the main thing is that the detachment is parallel to the regional depth of those horizons. And so it's a little bit, the nomenclature is a little bit confusing on that one. So what you'll notice is that we've gone in, we've plotted the fold areas. The software takes into account the displacement on all of those little faults automatically, and it's plotting up those fold areas as a function of depth, as we always do. And it's also giving us the total amount of shortening accommodated by all of those folds. But what you'll notice is that the computed detachment depth, so the linear fit right here, comes in too deep for the section. It's well below so this is thousands of feet. And so it's well below the sort of known, or at least interpreted base of salt, so the orange shaded region there. But it is a very good linear fit, which indicates that we have a very consistent interpretation in terms of maintaining fold area. And so this method actually, if you were to, for example, if you were unsure about the correlations in the structure and, potentially had placed some of these on different reflectors, and you have one particular point that falls off of that linear trend, you can essentially play around with those correlations until you get something that better, that is sort of consistent with the linear array for the rest of the points that you've established. So this can actually be used as a sort of dynamic tool for adjusting interpretations to improve the consistency in terms of area balance of the entire section. But as I was getting at earlier, before I derailed myself, was that the computed detachment depth is actually well below the rest of the structure. It's well below, where we would reasonably expect it to be. And that is essentially an effect of salt migration, or, if you're, depending on the setting, it in most general terms, it reflects a mobile layer that has essentially migrated material from the regional limit into the core of the structure, effectively shifting the array of all those fold area points in one direction or another. So if there's salt being injected into the core of this structure as it shortens, that artificially will inflate all of those area depth points. And then a consequence of that is that the projected detachment depth will be too deep. And so as long as you have some understanding of where the, sort of the kind of, maximum acceptable depth for the detachment is, you can actually reconfigure the area depth graph to allow for a variable intercept axis. So under area conservation, we assume that the intercept happens where there's zero fold area, and that's the detachment. So that's the case of those four models that we looked at earlier. If material has been moving around, you can actually change that intercept axis. So what we can say is that, well, I don't agree with how deep that is. So what we can do is change the intercept axis to be something more reasonable. And so what I'm doing right now is I'm shifting it looks like I'm moving that axis around, and what I'm actually doing is changing the intercept of the depth axis with my computed detachment depth. I'll zoom this in a little bit more, so we're just dealing with that structure. And I bring it to about where it is, where the base of the salt is in that interpretation. And so now what this is actually giving me is a positive area intercept. So we're no longer down here at zero where it was too deep. We're at a positive area intercept. And what that intercept, that positive area represents, is an estimate of the total amount of salt that is migrated into this section and into each of the cores of these folds. And so that gives us an estimate of how much salt migration has occurred. And this little narrow dashed line down here gives you the estimated thickness of that entire salt layer that would have moved into the section from the regional limits based on how much displacement. So this is a restored thickness of the salt that migrated would be about a 600 meter thick layer essentially migrated from the regional limits into the cores of those folds. And so you can actually take this one step farther, and if we, what I'll do is I'll put up our, I just drew a marker around the salt. It's not it. So there's our salt. So this is the shaded, we've shaded in the salt. And what you can try and do now is say, okay, well, this is where they've interpreted the salt. I can look at that salt, and so the area is shown. That's the second thing up from the bottom there, right above right click to exit in that box. So it's estimating about 50 times 10 to the 6 square meters of salt. And so that's actually more salt than what the area depth method is estimating. And so what that might indicate is that they've estimated or over-interpreted the total amount of salt down there. And so that then allows you to kind of go in and play around. And I think one of the things that stands out to me is that they have a very thick limb right here between the top of the salt and the green that then gets thinned out quite substantially. And so, maybe one scenario to play with is that if you change that salt geometry right there to be slightly thicker compared to, to maintain the thickness of that overlying layer. We can beat down the total amount of salt area. And so now that's down to about 44 times 10 to the 6 square meters. So it's still more than the area depth method indicates, but it's a way of kind of estimating how much salt would have actually moved based on the fold geometry that we've interpreted and the probable detachment depth that we can estimate from the seismic data. And so it's a tool for, kind of getting an approximation of what's actually happening with regard to the salt. Obviously, salt's a 3D problem, so it's complex, but this gives you a starting foothold on the problem based on the geometry that we see in the overlying section. So I'll finish up with a study on kind of applying area depth method in a larger kind of integrated structural context. And this is based on a presentation that we gave at AAPG in 2017 using the 2D Gigante survey from TGS. And so what we're looking at is a big long regional line from the Mexican Ridges Fold Belt, where we've got the Quetzalcoatl extensional system. So it's a large series of growth faults that then transition downslope into a whole bunch of contractional folds out into the deep water. So this is their multi-beam bathymetry data. So this is the region where we've got the extensional faults that are actively accumulating sediment. And then each of these ridges are actually folds that are interacting with the seafloor, so they're actively growing. This actually turns out to be a volcanic plug that the whole system is sort of sliding around. So at any rate, this is an example of how we might be dealing with, in a frontier setting, using area depth in an integrated context. And so we'll look at the whole regional lines. They've got a Miocene growth section in the Quetzalcoatl system that all appears to detach in a lower Eocene shale. So here's the Quetzalcoatl extensional faults. There's a rather complex enigmatic structure between the extensional faults and the contractional folds. The quality of the new seismic data is quite good, but it reveals a lot of structural complexity below each of those folds and kind of raises the possibility of maybe a mid-level detachment where some of these smaller thrusts are ramping up below those folds themselves. And then as we get out into the deeper water, so almost at 3 kilometers water depth, there's another change in structural style where the faults become much more subtle in terms of the amount of offset, but they are at the middle of these very broad, long wavelength folds. And so there's it implies a level of structural complexity that's fairly high. So this is forward modeling. And so basically we wanted to create a stratigraphic framework. And so we used structural forward models to get those correlations for the fold belt, for the extensional structures, as well as the relative sequence timing. So we're able to actually match those models to the data in the growth structures quite well, because in the grand scheme of things, these are actually fairly simple in terms of the kinematics. So we were able to use forward models to essentially estimate a total of 11 kilometers of displacement and begin to get correlations across the faults. The problem is that when you get to these transitional structures, the kinematics get pretty complicated. So you have a kind of a seamless transition from extension where we've got our interpreted footwall from the forward models right here and the correlation down here in the hanging wall. But if we draw kind of a tilted regional parallel to that underlying detachment, we see is that some of that fold is below regional, which is consistent with extension. But some of that fold is also above regional, which is consistent with contraction. And so that's kind of a mixed kinematic system that kinematic forward models aren't really going to deal with very well. And so this is a great place to apply area depth, because we can take this part of the structure that's easy to interpret. The seismic's really good. It's pretty straightforward up here. It gets noisier at depth, but we can essentially kind of avoid that. Just take the easiest to interpret horizons, perform an area depth analysis, and we get a computed detachment depth that lines up with the depth of the detachment from the forward models, and it's also consistent with what we're seeing in the seismic data. And we get our estimate of the amount of displacement and also some information about the kinematics. And so here we have this, the layer parallel strain values, and it's actually fairly high across all of these structures, but really spikes at the top of this green horizon where we have all of this noise in the seismic data. And so what that could imply in this case is that there's actually a greater degree of structural complexity at the core of this fold, potential imbrication that isn't necessarily reflected by how we interpreted that horizon. And so there's a lot of insight, but we're still able to kind of circumvent the complications of the kinematics to just get the detachment depth and the displacements without having to try and make a lot of assumptions in order to model it. So that allowed us to estimate the total amount of kind of net displacement on that structure. So, it's extensional and contractional, but what we found out was that by doing that area depth, the contraction kind of wins in that fold, and you end up with about 3 kilometers of net contraction across the feature. So then we kind of moved on to the fold belt itself. And again, that's pretty complex at the deeper level down here. So there's that possibility of a mid-level detachment. But at a shallow level, all the folding's fairly concentric. It's fairly easy to interpret. And so that really lends itself to our area depth work. So we take a stab at it. We set the regional limits at the syncline axes to capture that fold within that area. We've interpreted just a couple horizons. The interpretation stacks up on a nice linear trend, indicating that it's a good area balanced interpretation. And then the computed detachment depth is right there at that lower Eocene level that we know from regional information is a regional detachment, as well as that being consistent with where we had the detachment in the forward models. And so here the layer parallel strain is less, but nonetheless we're able to get at the displacement relatively quickly. And it also indicates that despite the fact that there is some indication of faulting at the core of the fold, there really doesn't seem to be a mid-level detachment, because we've got a nice linear trend that's consistent with this entire structure responding to displacement at a deep level. And so even if there are some detachments that kind of come out, all of that displacement appears to be contained within those synclines. And so you can apply the area depth method to each one of these structures individually, pinning them at the, setting our regional limits at those syncline axes. And then we computed the detachment depth for each one of them. And more or less, they all line up with the that green line being that lower Eocene detachment. That works all the way out into where we begin to get into those subtle, broad wavelength folds. But there is that change in structural style once we come off the, there's this dip in the slope. And, just in terms of balance in these gravitational systems, we often kind of think of, the total amount of extension needing to balance with the total amount of contraction in some broad sense. And what we found is that, for this 11 kilometers of extension on the Quetzalcoatl system, the total amount of shortening on those major ridges, including the transitional structure, only amounted to about 8 kilometers of shortening. So there appears to be a little bit of a deficit. But if we look at the bathymetry, there's a few more of those subtle structures out in the very deep water. And when we look at those, we're shifting to fold wavelengths on the order of about 20 kilometers. So those are the synclines. That's about 20 kilometers from that syncline to that syncline. And these are the ones with the very subtle faulting at the core of those folds. And so it's difficult to measure displacement on these things if you're just doing the bed length itself. So if we're looking at the tilted regional here, that's a very subtle fold. It doesn't look like a lot of area, but it's spread over about 20 kilometers. And so when you do the area depth analysis, it actually tells you that that's about 1 kilometer of shortening spread over about 20 kilometers, a 20 kilometer cross section wavelength of fold. And so if you were to try and estimate that from bed length alone, so these are the displacements estimated from the bed length, you wouldn't even come close. And so by looking at the fold area, that's the only way to truly understand how much deformation is going on here. And again, we're able to circumvent having to have a robust interpretation through the faulted region just by taking the sort of simplest part of the fold. And we get a detachment, computed detachment depth that in this case is slightly below the lower Eocene level that we were looking at earlier. But what's interesting is that now the seismic character in that region is much more diffuse. And so, you know, potentially we're looking at a change in lithology or increase in thickness of that mud. And so maybe a weaker detachment that's allowing for these really broad structures to form. But by doing area depth, we're able to show that there's about 3 kilometers of displacement on those big but very subtle folds that actually makes up the deficit. And so we end up getting a relative balance between the amount of extension on the Quetzalcoatl system that's sliding down that detachment and forming those contractional structures. And so that you know, gives us confidence that we've now got a fairly consistent structural interpretation for this entire regional line. So that is all I have for today, and I'd be happy to take any questions. Thank you.
Hey, thanks. That was a really great talk. Really enjoyed it. One question I have goes back to the area depth where there was a lot of salt movement, and your initial solution was much too deep. And because correlating subsalt is so very, very important, the deliverable you seem to have gotten out of there was an approximation for how much extra salt was in the system. And is this a technique that you can also use, do you think, to help, and you alluded to it a little bit, to help with the correlations of the sediment? You were showing, well, if we change the correlation here and there, we change the depth to the solution. Do you think that's something that could be systematized where this approach can help you in correlations in particular areas?
Yeah, so the question was if you can systematize changing correlations and looking at the area depth results to get a better interpretation. And, you know, to some extent, it doesn't even necessarily, we'll look at this because we can make it a lot more dramatic on a single structure. But as long as you have a fairly well-established linear trend and, you know, potentially a detachment depth that you trust, or in the case of the salt, at least have some, you know, kind of estimate of where the most likely detachment depth is. So it does require a little bit of outside information. But essentially, if you, you know, have a strong linear trend, when you look at an individual structure, if you have, for example, too much area. So what I'm doing now is I've changed the correlation down. So now the blue horizon has substantially more area than it did before. And now it pretty clearly falls off of that linear trend. Whereas if you have a correlation that's too high, you are essentially taking area out of that fold, because there again, we're measuring those fold areas relative to the footwall depth in this case. So now we have less fold area compared to the adjacent two layers. And so it's, you know, it requires having at least enough interpretation in there to, you know, be able to position things relatively. But, you know, the best case scenario would be that you've got, you know, the suggestion of a linear trend and maybe a location of the fault plane. And so you can see that, you know, here, obviously that breaks the trend, but also we're getting a computed fault location that doesn't match what we see in the seismic data. And so by progressively, you know, in this case, the trend being that there's too little fold area for that particular horizon. So then your options are to either change the, sorry, I'll drag the horizon, either change the hanging wall position And so you'll notice that we've changed the interpretation a lot, but now we've got a consistent, at least it's in terms of the fold area, the horizon, this blue horizon is now consistent in terms of or more consistent. It's obviously not perfect still, but you can modify it. So now effectively we've picked a new horizon for that level by bringing it in line with the rest, as well as getting something that fits with your seismically imaged detachment. The limitation in a larger setting like this is that you're dealing with many different structures in that case, and so being able to zero in on a single fault is somewhat more useful for that process.
One other thing, if you can go to the slide where you showed a strong break in slope between pre-growth and kinematic section. Remember where that one was. And yeah, this may be more of a comment than a question, but as an explorer, I'm always trying to look at where is my prospective reservoir going to be, and where those two different slopes meet. You're defining a boundary between two exploration plays. Below that, you would be looking, I suppose, for fracture porosity or something. And above it, you might have syndepositional factors such as winnowed sediment on a paleodepositional high. Do you have any thoughts of that, of how that could help an explorer? I see that as where those two slopes meet. That's pretty cool information you normally wouldn't have unless you made lots and lots of isotops. So any examples come to mind or thoughts where someone in play-based exploration would use this type of change in slope as a boundary between two separate plays?
Yeah, well, I think you've kind of got it right there. The implication of any of these trends where you have these linearly decreasing fold areas is that these were all deposited prior to faulting. And so, then sort of an inference from that would be that, their thickness is, aside from stratigraphic concerns, the thickness is relatively constant across all of those. So it's pretty much layer cake. Whereas once you get into the growth section, and you can see this in the seismic here, there's a lot of onlapping onto the structural high itself, is that then the thicknesses are varying quite a bit. And that, is part of the reason why you have this, that change in the fold trend, because now the fold areas are subject to the amount of growth that's occurred. And, the footwall the distal hanging wall and the footwall here are substantially thicker than they are at the high. So you have quite a bit more stratigraphic variation at that level.
Yeah, from a perspective of someone that uses PaleoScan a lot, and where I would have dozens and dozens of attribute maps, that type of slope information would be very, very important. Above the breakover where the two meet, I would see amplitudes. Perhaps I'm looking at some hard grounds, condensed sections on top of a high and a deeper water setting. Below and a bright spot might be a porosity development due to fracture development. So integrating that type of slope convergence, I think would be really helpful for a play-based explorer. Just a comment. Yeah.
Right. Well, thank you.
Yeah.
Oh, so we have a comment from the web. So the question is, could you comment on the consistency needed in the fault and horizon interpretations? And what happens if you have errors in horizon intersections? So as far as the software goes, in terms of the consistency, so how the horizons are interpreted, if we zoom in on the section. So maybe this has to do more with the second question being the errors. So the software is actually projecting these horizons forward into the fault and then finding the projection on the other side for the corresponding footwall for the horizon. So if we display the horizon intersections, the software shows us valid intersections with these little green circles, and it's giving you the amount of slip across the fault. So it does that for each of those, each of the back thrusts as well automatically. And so if we have issues with how that's been interpreted, the software is really good at getting the projection for it. So you can see that as I move around that green horizon, there really isn't, it's still measuring that fold area pretty accurately. If I actually change the geometry there, it will also change the measured fold area dynamically, but it's not really impacting the total solution very much because we've got quite a few other points, and that ends up being a relatively small change in terms of the amount of area with the new interpretation. Issues that may arise would be if you actually cross the fault. And so you can see now that the software has picked up a issue where if we go back to our intersection tool, so it's giving me a warning that the fault is actually intersecting the horizon within a segment. So that it's flagging that. And so this is the end of the horizon that it finds, but it's not projecting back into a fault, and that it's finding that there's no matched intersection on the other side of the fault for the underlying horizon here. So it determines that connection, but it flags that as an error. And so that's shown by these red and orange dots, and it's also shown on the graph itself. So if you're getting results that you're unsure about, it's always worth looking at those potential errors. Seem to have lost the display for the questions. I think the other one was about the consistency in terms of the interpretation. And so I think this gets to Steve's question a little bit, in that if you have horizons that are inconsistently interpreted in terms of the correlations across the faults, that's shown by strong variations off of the linear trend for individual horizons, as well as if you change the geometry for the fault itself, that will also affect the fold area. So this one's pretty well constrained at this point by where those horizons are, but you can see that as I change the geometry of the fault, we may get a different computed detachment depth. So in this case, like if the computed detachment down here is shown by that dashed line. And so if we change the location of the fault itself, it gives us different fold areas. So you can see that if in this case, you need that additional information, and if it's not consistent with the seismic data, the alternative is modifying the fault until you begin to get a computed detachment depth shown in blue that's consistent with about where you see the probable detachment in the seismic section. All right.
One more question.
Sure.
When you were doing the fault trajectory method, on at least one example, you first rotated the section to remove the regional dip, and then you came up with your solution. Once you have that solution, how difficult is it to then take that final fault estimate and unrotate it to put it back on the original side? Is that something you can do, or do you have to kind of?
Well, you'd have to. So the area depth graph is displaying the the results for the geometry as it is right now in the section. So it's taking those fold areas based on where the footwall intercepts regional limit, where the hanging wall intercepts its regional limit. So you can do the analysis in the rotated space, and then we can, you can either draw in a new fault, or, for example, if we just create a marker, what we can do is lost our area depth graph. Okay, so we'll set that as active. So you can actually draw out the kind of estimated path of the fault. You can do this across a series of sections or a series of analysis points. Sorry, Zoom keeps getting in the way a little bit there. So we'll redo our analysis right here. We'll draw another marker across that segment. And so this would be an example of if you had really no idea where that fault was in the basement. Just keep drawing these line segments in along the computed detachment location. Now if we hide our area depth graph, so now we've got basically a fault envelope for that deeper part of the section that we were looking at. And we can then rotate. So if you actually had this open and if you'd done the rotation in Structure Solver, I think I already closed the rotated. No, I think I still have it actually. So what we can do is send these back to the original section. Yep, and now this is our, and so there they are in the unrotated space. So this is our rotated section, and this is our original unrotated section that has the regional dip on it. So there's that kind of fault envelope that we created and immediately put them back. You could unrotate it as well, but that's our new tool in 4.1 is being able to move interpretation from restored sections back and forth. So they're linked now.
Well, thanks a lot, Nate. It was a really good presentation.
Okay, thank you. Thank you for your time. Okay. Yes.